So today's plan is building hydrodynamic equations, building stochastic, in principle, hydrodynamic equations from stochastic microscopic models. And I could do many different cases. I'll do the case which in some ways is more subtle than the usual flocking equations. I'll do the case of the active nematic. The reason is, so if you recall, remember we've talked broadly about two kinds of models. We've talked about polar, we've got polar systems, which is V-check, donor 2. And you had these funny apolar things that we talked a fair bit about in the last lecture or so. And in these systems, the main result of activity was that the order parameter is a velocity field of a kind. And so the consequences of activity could have been guessed at just by saying, well, I've got a bunch of particles. If they line up, that's a velocity. The form of, the way activity enters the coarse-grained equations of motion is relatively obvious without a lot of fancy footwork. Basically, you have that, try to stick to the same notation. The order parameter just comes in here in the form of a drift term. The funny thing, and likewise in the order parameter equation itself, the funny thing that happened here is that I argued sort of by trying to draw cartoons, pictures and whatnot, that what's special about these systems schematically speaking. And I don't think I necessarily sold this very convincingly to anybody. You can take the point of view that we are allowed to write down whatever isn't forbidden, and we are not in equilibrium, so we are even more liberated than usual from those constraints, and therefore a term like this is possible. Then I drew you some cartoons and said, look, you've got a curved region. If you've got stuff that's straight like this, that doesn't have a polarity, it can't go anywhere. But if you have a curved configuration like this, or like this, that has a polarity. So no polarity, no velocity. These things should have a velocity because they have a polarity. But I didn't do a calculation that brought out this term. The interesting thing about this term is this term comes out of the mean motion of the individual particles. This term comes in a weird way only out of the fluctuations of the particles. And that's what makes it so cool. And so what I'll do is I won't do a painful derivation of the full form of the equations of motion for an active nematic. I'll tell you how this term arises. And once you see it, you'll realize it's obvious. But it's cool because it really is a purely noise effect. Yes? I already remarked in this earlier lectures, you can have a diffusion term, you can have a noise. I think it's purely historical that Toner and Tu took the point of view that we will only deal with a density field and a velocity field. The velocity field was being included because it was the order parameter for the problem. They could have, and their idea is, look, let's declare this object to be the velocity field. In that case, that equation is an identity, right? in principle, in a sense, that's okay. The reason that's okay is this. You're trying to write down only the slow variables. Okay? If you have a system without momentum conservation, which is what Täuber and True are writing down, you only need to include that velocity field because it's the variable that orders, not because it's a conserved momentum density variable. Remember, Täuber 2 describes particles in contact with some kind of passive damping medium. It's not bulk fluid dynamics, right? So you've got a density and you've got this variable which serves both as an orientation field and a velocity field. So their point of view was, that's it, we've done the slow variables. And if we deliberately choose the total velocity field, the barycentric velocity field, whatever you want to call it, as the variable, you don't have to include any other terms. You could take another point of view. You could take a point of view as, I'll choose the orientation variable of the particles. Okay? I've got a particle where S is actually just the particle's orientation. It's not absolute that the particle's velocity, the particle's displacement has to be always orientation times delta t. It can also diffuse, right? And then you could have something else, but in fact, the slow variable accounting wouldn't change because there's no momentum conservation. You aren't adding a new slow variable. The velocity, you would either slave the velocity to the orientation or slave the orientation to the velocity. However, there are some complicated situations where you might accidentally set to 0 something which is generically non-zero by this absolute identification. But offhand, I can't think of anything. Okay, that's the reason you didn't do it. You could do it and you wouldn't really get anything new, and at least you wouldn't really get anything new in either case. Okay, supposing you're in the isotropic phase. Okay, let me digress. Before I go to the main story, let me digress and tell you a little bit about this. Supposing you take the Täuber 2 model and work in the isotropic phase, okay? You got ds over dt equals various terms, one of which is just minus alpha times s, various other terms, one of which is, I hope I have my signs right, minus something times grad rho, etc. Okay? So supposing you're in this phase where s isn't ordered, then you can do a purely linearized treatment of the relaxation of s. And you can go to the longest wavelengths. In that case, at times, on time scales big compared to 1 over alpha, S is approximately minus B over alpha grad rho. Okay, and let's say plus noise. Okay? And let's give that noise a name. It's a vector. So then what would happen, I could take this guy and put it in here. And among the things I get will be diffusion. And will be density fluctuations consistent with diffusion. So actually, if you're in the isotropic phase, it works out in this way. If you're in the ordered phase, still the longitudinal component of S, the component of the fluctuations of the order parameter along itself, will be fast. They will again get slaved to the density and to the transverse things. And the effective dynamics of rho will always get some diffusion, even if the apparent form of the equation of motion. In other words, you can think of this as just a way of writing the current, and it becomes a question of whether you want to call everything in there the velocity, or you want to separate out stuff. So what I want to do is to tell you a bit about how this term has got a name. It's got a completely boring name, curvature-induced current. And let's, from the way it's written, you would think it has to do with the fact that, look, this is a liquid crystalline phase, you're introducing a curvature, there's some mechanical consequences of that curvature, like stuff trying to straighten out. Turns out that this doesn't come from that at all. It doesn't come from any of the mechanics. It comes only from the statistics. And that's why it's cool, and that's why it's nice to talk about it in a statistical mechanics course. Okay, now, of course, I have to be able to read what I've written. Actually, I should have, since Abhishek was nice enough to ask a question, are there other questions before I get into this about last time's lecture? Especially from those of you who weren't at last time's tutorial. Says snidely. So I don't need to worry, you guys understand everything. No answers. Don't all shout at once. No other questions before I go further? Okay. Let me tell you about the two kinds of I'll tell you a little bit about the microscopic model for this guy and for this guy. Then I'll concentrate on the microscopic model for this guy and tell you how this comes out. I won't trouble to tell you how every term in the equations of motion comes out, because this is the only really interesting term. Okay? All right. So let's start with the VIII model. So this is not the nematic, this is the polar guy. So the idea is the following. You've got particles. Each particle has a position which I'll call xi and an orientation which I'll call ni, which is cosine theta I, sine theta I. Okay. And the dynamics of this system is theta I at time t plus 1 or t plus delta t, let's say, is the argument of the complex number sorry, this notation is just to be consistent with the notation in some papers in the subject. The angle at the next time instant has two pieces. It looks, basically here is my particle and here, smaller so I can draw a neighborhood. I'll call that the neighborhood of I. And by neighborhood of I basically mean something with some radius, some name, R, okay? And it will look at all other particles, particle number J, particle number K, and so forth. And so what I mean by this sum is all these guys in the neighborhood. Okay? This is a parameter of the model. And by itself, it doesn't have any physical significance because these particles I'm treating as point-like. It has a significance only with respect to the time step. So if you like, I mean, the distance it steps in a unit time interval. Right? It's that ratio that means anything. So this is what the angle does. And the position, oh, I haven't said what this is, sorry. So this is quite clear, right? The sum of these unit modulus complex numbers is a complex number, which is not necessarily unit modulus, right? And you take its argument being the angle. No, including itself. If there are no other neighbors, it won't know what to do if it doesn't include it. No, it looks, what is it doing? It's taking a bunch of unit vectors and adding them up to make a unit vector. If this particle has no neighbors, that unit vector is itself, and it will remain unchanged. Sorry, I must be making some mistake here, which I'm not getting. Neighbors. I didn't say excluding the I. I didn't say excluding the I. So I don't exclude the I. Right? I'm just saying that you need to take care of the case where no other neighbors. You won't know, there won't be a, no, theta, the new angle is simply obtained by forging a local consensus and finding a new angle. Yeah, you could do it other ways, but this is, in these discrete time, it's the easiest thing to do for, meaning that, by the way, there are any number of ways of doing it, right? The other way of doing it is to introduce a torque proportional to angle differences. The other way of doing it is to have collisions. You've got two particles going like this, and you make a collision rule. There's many different ways of doing it. And, as far as I'm concerned, for most purposes, it doesn't matter which of these. Yeah, right. Yes? Okay. I know actually many people, given what they're familiar with, would have preferred that I start in lecture 1 with this and then build. but I'm doing it first. All right, but this, what is this? This is angular white noise. For example, I mean, you could think of many things. Again, the central limit theorem tells you that you could instead say it's going to just change the angle this way or this way by eta. Here I'm taking angular Gaussian white noise. And let us say this is unit strength, so that measures the strength. You could do it many ways. Okay. So what do these particles do? These particles try their best to align with each other, and they make some error. So the two important parameters in this model already you can see are the error and the local population density. So let's say mean number of particles in the neighborhood or mean number of particles per unit area, volume, whatever a system are the two important variables. And this is what Abhishek did in 1995. Oh, sorry. And xi at t plus delta t is well, do I do ni of t and I have delta t? Hardly matters. I think in the standard versions, it's ni of t. No, nothing. That's the point is that these are particles in contact with some path. The coarse-grained noise in the PDE will depend purely because of how you build the noise. And that's one of the things I'll tell you about today. This thing that Dean showed, for example. Yeah. Yes. Yeah. No, arg is just your complex arg. There's amplitude and arg. No, the word argument. So no. It's trying to, it's a kind of average, but there's more than one way you could do the average, right? You could do the average by summing all the vectors. You will get a vector whose length is not unity. And all you're doing is, you're not bothering to normalize it. You're just saying argument. Argument just means you write it as a complex number, rho e to the I phi, and arg means just phi. That's all it is. So it's literally what you're thinking. You've got a whole bunch of vectors. You can take their sum or you can take their average. It doesn't matter, right? It's because that only changes the prefactor. The phase, the angle, this is that angle. Well, it's persistent, right? Because the particle, the effective velocity of the particle will be persistent, right? Because it's going to move in the direction in which it is pointing. Right, I'm saying that supposing you didn't have the alignment rule, supposing you just had this. Supposing you just had this, what would you get? You would get x dot of each particle is equal to V0 times unit vector of each particle, right? So I'm saying supposing you don't have the interaction step, you only have this. This isn't it's a persistent random walk, because n hat, this is theta dot, is, sorry, my notation is getting bad, I. Right? So the fact that the velocity, this is an Ornstein-Uhlenbeck velocity, not a Brownian velocity, because the angle is doing a rotational random motion. And I'm not making the velocity do it, the particle's displacements do anything other than step in the way in which they're pointing. So it is already a persistent random. Each individual particle, in the absence of other particles, precisely executes a persistent random walk. And what you'll find is that, basically, that this or this squared over 2 or whatever it is will give you the rotational diffusivity, right? The rotational diffusivity is eta squared over 2, right? Right? Yeah. So what you will find is that the velocity will decorrelate on a time equal to 1 over dr. Right? So, if you actually take the particle velocity, if you had no other particles, right? So it's actually persistent at a single particle. Oh my God, yes. It could be, but I'm doing NFT. This means the update to this n happened to the previous time step. Actually, I don't think my derivation is going to actually be sensitive to that, because I'm not going to give you a derivation. But meaning when you actually carry it out, it does matter, it will change some things. you could do it either way. Yeah, so this, by the way, this model is VIII 1995, VIII et al. 1995. The coarse graining as a paper in 2006, I think, in Physical Review E. What these guys do is to take this, and you know, now you basically, even though these are not particles which have inertia, because they've got persistence thanks to this angular field, you can do something that looks a lot like a Boltzmann equation. Right? You've got a position and a velocity. And you can define a one particle distribution of position, orientation, and time. In the obvious way, this is the probability density for finding a particle around x with angle theta at time t, right? And you can evolve it. You can build an evolution equation for this, and from its moments, you can get the equation for the density and the equation for the velocity field. So let me just state what those moments would be. So, you know, I'll call this rho where this n is just cosine theta, sine theta, treating theta as the argument here. And you can build, you'll get quote unquote hydrodynamic equations for this. I haven't told you all the real difficulties. The real difficulties, okay, so say one thing. Yeah. I think in this paper, the way they did the derivation was not through this step, but rather through a collision step. See, you can imagine thinking of your particles as actually rods of some size. Okay, and they move until they hit each other. They move with this velocity plus a noise, and then upon collision, you can make up a rule about before and after, the way you do in mechanics when you go from kinetic theory to hydrodynamics. Okay, I think much of the derivation here is done that way, but that's a matter of detail. Sorry, you have a question? Right. Yeah, but then it'll just order. By this rule, without the noise, it'll just order. You'll eventually find everybody pointing the same way. No, I'm saying by collision, I have to give you a different rule. I don't give you this. I have to give you a rule for before and after. I have to give you some probability of outcomes. You could do it. You could actually put in interactions that depend on the angles between the particles and on their angles with respect to their separation vector. You know, meaning you can do the kinetic theory of anisotropic particles, or you can, I'm saying there's many levels of description. But in fact, that's actually not the most interesting part of this. And the reason is that all of that is a lot like just hard-rod kinetic theory to make a liquid crystal, to make the dynamics of an oriental fluid. And that's actually not where the cool stuff arises. So, you know, when you of course, so I'm saying, that's why I said Boltzmann equation. I'm saying that when you derive the equations of motion, what you do typically is you make the same ansatz that Boltzmann did of all of you, yeah, molecular chaos thing. There's no, you know, it's kind of justified anyway because these are anyway noisy systems. Okay, you can, why does that change anything? You can derive the hydrodynamic equations for a liquid crystal with stress. Because that's talking about, see, first of all, I don't even want to get into the degree to which the Boltzmann ansatz is justified. The point is you can, when you do kinetic theory for liquids, liquids are also highly correlated systems, right? So you can still build those equations. Or you can take another point of view that what you're going to do is build the analog of operator equations of motion. You're going to build stochastic PDEs. So when you do that, when you write down density times density, you don't mean mean density times mean density. You mean stochastic density field times stochastic density field, maybe separated by some distance. And then all the work of working out the correlations has to do with solving the dynamical field theory that you are presented with these equations, right? The part of the problem, I'll tell you, supposing, sorry, this will take me on a long digression, maybe we can talk about it later. Yeah. This is the distribution, the one particle distribution function. What is one particle distribution? It just means, it doesn't mean the system has only one particle. It means you're asking what is the probability of finding a particle? What is the probability density of finding a particle around x, theta? A particle with orientation theta around x. So you must have done Boltzmann equation, kinetic theory. Have you done Boltzmann transport equation with positions and velocities? Same thing with positions and angles. Because in this problem, the angle with which a particle is pointing is telling you the velocity with which it's going. The speed, I've taken a very simple model, right? The speeds are constant. So which way it points is which way it goes. And it goes at this speed. So it's exactly what you've done in Boltzmann transport equation. The only difference is where these are particles whose speeds are specified. Collisions do not change their speed, they only change their direction. And, okay. But as I said, what I'm going to do, I'm just going to assert that you can look up how these guys derive the equations of motion. The reason I'm not doing it is that I want to tell you about the apolar case. I'm not going, yes. F has exactly the same status as the distribution function when you do kinetic theory. This is the kinetic theory of these particles. Coarse graining has to do with certain steps you take when you build these equations of motion. Okay. You'll see that. And actually, there's two ways you can do it. One is actually to derive the equations only for the average quantities. And the other is to say that if I have n particles moving stochastically, their density, even when I coarse grain. Remember, what do you do when you coarse grain? You've got a system that big. You've got particles this small. You pick a scale in between. That means, supposing I take a region of this size, and I've got some particles inside it. The number, and let's say I've got, what is the mean number of particles I have? Supposing this region has size R, and supposing the macroscopic mean number density of the system is rho, then this region contains, on average, rho times pi r squared, if I'm in two dimensions, particles. But that number is not fixed. That number will fluctuate by, right? And that means if I define a field, a number density field on this scale, this is assuming no other effects. The purely statistical part of the fluctuation is this. So if I define a number density field, I really should be thinking of a number density field whose dynamics evolves not only systematically but also randomly. The partial differential equations I write down for the number density field should be stochastic PDEs. And stochastic PDEs you already saw. You saw them probably in your lecture today or not, because I wasn't there. And certainly in Uwe's lecture earlier, last week. And the reason is really this, because you coarse grain to a finite scale. Fluctuations vanish only when you coarse grain out to the whole system size. It's only then that the mean thermodynamic kind of behavior sets in, right? So strictly speaking, these things are fluctuating quantities. Okay. So what I want, so these guys, as I said, carried out a derivation, and the end result of their derivation was the equations that Toner and Tu wrote down. Okay. The difference is that every one of the coefficients there is now not dreamed up, but calculated from this microscope. Not a silly question. Well, I mean, yeah, it's an equation of distribution function in both cases. You can think of them as similar. Normally, when you write down a Fokker-Planck equation, you start from a microscopic stochastic description. Normally, when you write down a Boltzmann equation, although not here, normally when you do the Boltzmann equation in kinetic theory, you start from a microscopic description which is just Newtonian mechanics. Right? So they are different. So usually when you use the word Boltzmann equation, so here you have to be a little schizophrenic about, a little confused about which to call it. Okay. You call it because, especially in this case, you know, the microscopic equations are Langevin equations with this funny term. So it becomes only a question of terminology. Usually, I think the reason these guys call it Boltzmann is it looks so much like positions and velocities, and the change of orientation happens through a process that so resembles collisions in a, in gas or liquid. I say, look, this is our Boltzmann equation. I think the important point is both the Boltzmann equation approach and the Fokker-Planck approach are different from building coarse-grained but still stochastic equations. As you will see today. Today, I'll take n independent particles. One of the exercises I'll do is I'll take n independent particles, no interaction with each other. Each is just doing Brownian motion, not talking to the others, and ask how does the density, number density field of that system evolve? And you will find a stochastic PDE comes out. It's the diffusion equation plus a noise rather than just the diffusion. So I'm saying that I would say that's truly different from either Fokker-Planck or Boltzmann. Because you're looking at a quantity which normally you would be tempted to average and call the probability density of finding the particle. Right? So I'm saying that it's the difference between having one particle and writing down the equation for its probability density and having n particles that don't know about each other and writing down the equation for the number density of that system. You might think they're the same because you're taking n copies of this guy, but they're not the same because I rubbed it out, because the number can fluctuate. So that's different. Yes. No, you need to do more. The point is, regardless of what the microscopic dynamics is, the reason you need to make this assumption is because you're asking for the probability of a collision taking place. The probability of a collision taking place is the has to do with the joint probability of having a particle somewhere and a particle somewhere else so aligned as to have a collision. And that's a two-particle distribution function, regardless of whether the microscopic description is stochastic or not. And it's in taking a two-particle distribution function under some circumstances and replacing it by the product of the one-particle distributions. That's the assumption. And it doesn't matter whether the microdynamics is stochastic or not. By the way, the one equation you can check very quickly for yourself with these definitions is this. It doesn't require a derivation. Check that this follows an identity, okay? And it follows because in a continuum picture, x dot is just v naught n. I won't do the other one. I'll just tell you that they derive toner 2. Where is it on? I'll come to why. This work was, by the way, this work is important for many reasons. One is just showing that you can get those equations. The other was that when they did this, they calculated those coefficients and their density dependence. Now, when you say a coefficient is density dependent, you don't mean it's dependent on the total number of particles in the box divided by the total volume of the box. You mean it depends on the local density. So every one of those coefficients that you're treating as a constant is in principle a fluctuating quantity. It depends on the local density. That's equally true for the air in this room, you name it. But sometimes it matters fatally. Okay? It turns out in toner 2, that density dependence, which I think everybody who wrote down the equations knew about but didn't worry about, has many interesting consequences. If I have time today, I'll show you one of those consequences later on. Okay. So the first fun thing we're going to do is to modify this process for apolar particles. Okay? I don't even call it. Let's just say apolar particles. And the trouble with apolar particles is not that you can't assign an orientation. The trouble is that they don't no forward from back. What's an apolar particle? An apolar particle is a particle without that arrow. Okay. So what I have is one of these guys. Let me rub all this out. So I can still, I can take each particle and I can color. I can color one end of it yellow, but not change anything else. I've just colored it. And why I color it is, what I mean by I can color it is I can give it a unit vector. Right? If I have a rod with neither head nor tail, unless I know which end is which, I can't even ask the question, what is n? Okay? So let me color one end of it, and that coloring doesn't change its interactions. Okay? Its interactions are without polarity. I can still write n as cosine theta, sine theta. But when it interacts with its neighbors, it doesn't know about theta. It doesn't know the difference between theta and theta plus pi. Okay? So what I will do is I'll say, if I get this right. Okay, so what did I change? I put a 2i there, and because I put a 2i there and I still want a theta to come out of it, I better divide by 2 here. Supposing I had only my particle, then the argument of this guy would be 2 theta, which is kind of stupid. So I have to divide by that. That's actually, of course, even weirder. This is okay. This is fine. This is just, okay? And what happens to x is, so that little step, now let me just, I just look at my notes to fix notation, okay? I don't want to write a V0 times a delta t for reasons that I'll make clear in a moment. Actually, let me just write it this way. This is, if you like, let me stick with the earlier model, okay? I'll keep the V0 delta t for the time being. But when I say V0 delta t, you should by no means think that these particles have a velocity. The reason they don't have a velocity, yes? Yes. You shouldn't go to options, definitely. The reason is that V0 implies the velocity. There's some persistent speed to assign a meaning to it. In practice, what you'll find is that the value V0 doesn't come into it at all. So let me just say, I'll put a step. Easy. Okay. So what have I done? I've said, and what do I mean by plus minus? I mean that with probability half, you get plus, and probability half, you get minus. So what am I doing here? I'm making a very strange kind of particle. I'm making a particle, supposing you were doing, Brownian rods. This would be a rod which only moves along its length. Which, of course, if you had a system with equipartition, could never happen. Right? Supposing you were keeping track of particles' position and momentum, then certainly this would never, this is not something that will happen at thermal equilibrium. So this is the only real modification. Okay? And this completely kills any physics of polar order. But you can see that it's a strange step, because it's making particles that preferentially move along their length. Now, an important point here is the following. You could weaken this. You could say, with probability, let's give ourselves some other, let me give myself more space here. I could imagine doing, you've got this particle, I can make it move like that or like that with probability p over 2 minus p over 2, and I can make it move like that or like that with probability, oh God. That adds up to p, that has to add up to 1 minus. So 1 minus p over, have I done it right? If I add these two, yeah. So I could have, huh? Oh my God, sorry. Thank you. I can have a particle that moves along its length with total probability p, transverse to its length, total probability 1 minus p, and I can have it unbiased. You can imagine cooking up many things intermediate. You could imagine a particle that moves slightly more that way than this way. You can interpolate between isotropically moving particles and these guys. You can do all those things. But for simplicity, let's take the extreme case where it only moves along its length and forward and backward with probability half. I said, for simplicity, let's take something that only moves along its length. You can do other things. I mean, if it moves at an angle, then you tell me what angle and so forth, right? You can also add to this. You could add plus purely isotropic steps. You can do all that, right? Yeah, you could do it. I'm sorry? Yes? No, I'm trying to emphasize that in the case of particles that move forward and backward with equal probability and have no persistence, it is not at all like a velocity. In the VIII model, where these particles have some sense of direction, it comes in like a velocity. That's why I said, we wrote down a Boltzmann equation. I said each particle has a velocity V0, a speed V0, it has a direction n. That direction n changes on a time scale 1 over dr, where dr is rotation. There it's meaningful to talk about it like a velocity. Here actually it turns out it's not at all a velocity. So the real surprise. You can see, what are the tuning parameters? You tell me. Yeah. Yeah. Theta affects n. Theta affects, no, n, come on, n is here, I've defined it. Yeah. Yeah. Theta and position and x and theta are also coupled, because you know who you have in your neighborhood depends on where things went. So they're very much coupled. It's not, you know, it's only slightly different from the equation of motion for interacting Brownian rods. In fact, for this particular problem, if I allowed the particles to move isotropically, that turns out to kill all the interesting physics. It makes it basically into a very simplified model for Brownian orientable apolar particles. And actually, when you lower the noise or increase the density, you get an aligned phase. And that aligned phase has all the properties of an ordinary thermal equilibrium, nematic, liquid. So that limit is cool. It's a little harder to find another limit which is also physically desirable, which is, you know, supposing you take a nematic liquid crystal. It's made of elongated molecules. So it's even at thermal equilibrium, the motion of any one of those elongated particles is different along its length and transverse length. Everybody knows that rods have something like twice the mobility along to transverse. If you do Stokesian hydrodynamics and you have one rod, there's roughly a factor of 2. That means the diffusivity this way and the diffusivity this way are different by a factor of 2. Within this very simplified class of models, I don't know a simple way to put it. I have to mess with the model a lot more if I want to retain the anisotropy of the motion, but not spoil equilibrium. That's more work that I'm capable of doing. So in these simple models, what happens is you kill the anisotropy of the motion, you kill the non-equilibriums. The two things, the anisotropic diffusion and the weird curvature-induced current, come with the same coefficient. But that's because this model is sort of ultra simple compared to other models. Generically, that shouldn't happen. So we won't do any of this. Oh, there's a paper written by a whole bunch of us in New Journal of Physics in 2013 by Eric Bertin, and then among others, my former student Shraddha Mishra, myself, various others, which spells this out, the entire business of deriving the coarse-grained equations for a nematic, active nematic from this model. Yeah. Right. So in particular, it's actually no use even asking what's the velocity field, because n and minus n are the same thing. So I can't, you know, if I ask, can I define a thing called, can I take the distribution function of theta, x, theta, and t, and multiply it by n of theta, and average it, integrate it over theta, and get something? I'll never get anything but 0 for this. Because n and minus n are the same thing. So this guy is equal to this guy, and this guy stood on its head are the same thing, so it's 0. So you don't have a velocity field. You only have a very weird kind of diffusion, and that's what we're going to try to understand. Okay. So what happened with my notes, I was writing my notes in a very strange way, so that the pages are out of sequence in an irreducible sense. That is, I have to peel off one side of a two-sided piece of paper to order them correctly. So when you can do that, and I guess we can try to scan it better. So what's going to happen? Let's forget about all the rest of the dynamics. Supposing we just want to know, okay, there's three things going on, right? There's alignment, there's randomization of direction, and there's movement along the length. I'm making the translational part of the dynamics very, very simple. Just this, okay? Let's ask what happens only as a consequence of this. The reason is the following. What will this give you in the equations of the orientation? It's going to give you a randomization of direction. That means if you start out in an aligned state, it will tell you how the system relaxes to isotropy. That is, it will just give you rotational relaxation. I won't even bother working that out. You can read about that. What will it give you? It will give you something that's relatively complicated, but actually familiar, which is it will give you the physics of how collections of particles with aligning interactions end up aligning. Okay? So what you will actually, I can just tell you what you will get from the aligning step. Will lead to, if I build an equation for the Q tensor, the orientation tensor that we talked about last time, etc. This term will basically give you this. And the reason that's the case is not very different from what happens when you start from a kinetic Ising model and try to build time-dependent Ginzburg-Landau. Okay? You get the terms that promote ordering, and you get the terms that promote alignment of neighboring regions that are particles. Okay? That's all that will happen. I won't do it. There's really no difference between this. Okay? And the coefficient of this term will be a competition between the noise strength and this interaction. And this interaction term doesn't have any parameter in front of it, but it has the number of neighbors. So it has the mean density. Right? You understand this, right? Normally you put in I could have put in a torque. I could have said this guy aligns with it with a torque which depends on some interaction coupling or something. We've simplified it and just say they align. So the only thing that determines the strength of how much they align is how many they are. Okay? So what you will get is one term with the density and another term with no density. And if you increase the density or decrease the noise, this A will change sign. Will do something like this as a function of rho. At some point, A of rho will become negative, and that within a mean field picture will mean that the state Q equals 0 is unstable to the spontaneous appearance of Q. But there's nothing novel in this. This happens in any microscopic model in which you put in a competition in alignment and noise. Okay. So I won't do this. So that in effect takes care of this. All right. So let's only work on this guy. So you can see what this will do. So let's just work it out. So how do you, supposing you ask, think, how does F change in a time delta t? How do particles come here? They come here through this process. They come here if this process moved them from somewhere else to here, right? So I claim I'm not putting commas and stuff everywhere. What I'm saying is that F has the form it has at the present moment, because if you think of the single particle level, there's a particle here now through this process, because it was a distance, it was plus d0 or minus d0 away in the n direction. If this is the only process I'm looking at. Have some subscripts here. Okay? F is the distribution function in x theta space. Okay? So when I say n, I mean cosine theta, sine theta. Right? And I claim that actually this is all you need to get that done. Which is a little weird. You will think, wait a minute, where did nematic order come from? Trust me, this is all you need. Because if you expand this to second order, so let's do it. Yes. True. But if I want to work out the, that's true. But supposing I'm interested in the evolution of the density, I integrate over all theta. So any of those terms, if I'm integrating over all theta, will not affect the density dynamics. So what I'm really interested in is d over dt of integral d theta f of x theta t. It won't depend on theta, but there'll be moments. There'll be n integral. Let's just do it. Okay. So the claim is this is approximately d0 squared over 2 delta t. So this difference, I guess I should really say. Let me just expand this out. Let me expand this out. And let me just average. Let me do the integral. Okay, let me not yet do the integral. Let's just. All I've done is to expand this. So at second order, this is what I'll get. Or at least that's the only term I'm interested in. But this is, so what I'm trying, actually let me say it differently. Supposing you didn't have theta, so you just had particles displacing along a fixed direction. Then the evolution, if I had just this plus minus going on, so what have I done? I've averaged over this process. Okay? So all I'm doing is saying, let's think of particles moving along a line, but that line has an orientation dictated by the local orientation n. And on that line, these particles are moving forward and backward. The reason it becomes an interesting dynamical term is that this line n is dynamical. This direction n is dynamical. And when I integrate this over theta, I get nn f of theta integrated, which is the local nematic order parameter plus a purely isotropic piece. Right, so what picture is this. Here is a direction. That's, at the moment I've specified n that way. If I just have particles hopping along that, I get diffusion. Now, all I'm saying is let that direction be something which is also evolving in the system. In that case, if I take only the process of moving along the local n, then all I get is this modified diffusion term. This is just del squared f along n. Okay? No, I don't need a dt because I haven't yet divided. All right, excuse me. Yeah, d0 contains a dt. No, but okay. No, eventually when I divide by delta t, no, but d0, this is actually v0 delta t here, right? So I think I've done it correctly. Let's just check. I think at the moment this is right? I guess I have to have a dt outside, don't I? What do I have to have? I probably want a dt outside, okay? And then when I divide, is that right? I'm really bothered. No, I guess that's correct, right? I'm doing something wrong here. I'm doing this, excuse me? I'm okay. I'm sure I have some. Be that as it may, this part is okay. Okay, I will work. I know in a course in time-dependent stat mech, I should get these DTs right. I will if I'll see if I can get the factors right when I'm done. Let's go to that. No, I know, but with the object as written down, that's all true. There should be. Yeah, so I yeah. Yeah, so I'm just wondering, so this contains, this contains df over dt and the diffusion part. So yeah, so, excuse me. Yes. Yeah. No, but D0 isn't something of order 1. I'm thinking of this as having, because this is a back and forth object, ultimately its effect has to come in at order square. It has to be thought of as a square root of dt object, which, right? Because I'm saying this is just diffusion. So I mean, supposing I did it without the ends, I'm sure we can do this right? So do this without the ends and then put in the ends. The ends only tell you the direction of the space. Okay? So it's whatever I would guess. I forget about theta. I have f of x t plus delta t is f of x minus. So when you do it that way, you'll get all the dt's, right? And I'm sure when I do it that way, I'll also get all the dt's. So the complication here has nothing to do with the fact that I'm keeping track of n. It is just that I was being sloppy somewhere about that guy. So if I said x of t plus delta t is epsilon, is x of t plus epsilon, then epsilon squared would be of order dt, and you would get ordinary diffusion. So all I'm saying, I don't know about this at the moment. I'm just completely perplexed. Okay, all I'm saying is that this process is exactly diffusion, but along a fixed axis, and it will come in with 2 powers of that axis. And because it comes in with 2 powers of that axis, if I now say this is taking place along the locally defined n, I'll get a quantity which, when integrated over theta, is the second moment of the theta distribution with respect to okay. And what that means is very interesting, right? Yeah. That's how it will work. Yeah. So I won't work out the rotation, diffusion, and the collisions. I've spent much more time on this than I wanted. Okay. Yeah, maybe I'll just. So now look at this object. Supposing I take this and integrate it over theta from minus pi to pi. Minus pi over 2 to pi over 2, sorry, because this theta is already because of these. Let me define call this f. So I'm choosing a notation where this k actually already has, and I've put a 2k here. So if k is 1, it corresponds to m equals 2, whatever you want to call it, circular harmonic order. I've already folded the 2 in here. So I'm completely I don't have anything polar. Everything is has got this theta going to theta plus pi symmetry built in. Okay, yeah. So then what will happen is that if I take this guy and try to work it out, if I take this nn, I can write this as, so just take this guy multiplied by e to the 2ik theta. So under this same Fourier transform, this term will give me, let me write it in two pieces, okay? Just for my convenience. Times F. Excuse me. I want to write it in this way because I want to separate out the piece corresponding to the pneumatic order parameter and the isotropic piece. So this will end up becoming half the Laplacian. This piece will give me just the Laplacian because I've got d alpha, d beta, delta alpha beta. And this piece will give me something funny. So let's see what it gives us. And the thing to note is because I've got these n-n's, I'll get cosine 2 thetas and I'll get cosine squared thetas and sine squared thetas from here. Okay? So that I will get f times e to the 2i k theta times some further cosines and sines, as a result of which I'll get k plus 1 and k minus 1. And remember, k is, in this notation, k equals 1 is apolar order, k equals 0 is isotropic. I have no vectorial order in this description at all. Okay? This will end up looking like this. Let me use a different notation. I'll call it delta. Delta is the usual Laplacian. I'll tell you what I mean by this. Where grad in this case is this. Star why does this happen? As I said, it's because you write n alpha and beta component-wise as cosines and sines. And patiently, work all this out. But if you translate it back into the language that we used earlier, let me introduce a notation. I shouldn't go beyond this, right? Let's define this object. And what is F1? F1 is what I get when I put in one factor definition. F1 is integral d theta f of x theta t cosine 2 theta comma sine 2 theta, or cosine 2 theta plus I sine 2 theta. It's integral d theta f of x theta t e to the 2I theta. That's F1. Okay. So let's define these objects in this way. Let me define a matrix with components W11, W12, W21, and W22, which is just what you get by another way of writing it is to say that it's just the nematic order parameter matrix that I talked about earlier. And these terms, if you then rewrite them in terms of averages of NN, these will give you, okay, supposing you do this for k equals 0. Supposing you take this equation and calculate the k equals 0 guy. Then what will you get here? You will get the k equals 1 guy. Here you won't get anything because there is no k equals minus 1. Okay? And here you will get del squared f0, which is rho. So as a result, you will get exactly so if you look at that equation for k equals 0, and now absorb del d squared over tau and stuff. Where gamma hat, the matrix gamma hat is okay. And yes. Right. Yes. So I'm saying that actually, okay, so if you go to higher orders in gradients, the effects of the interaction, okay, the effects of the interaction enter in two places. They enter the equation for the orientation, and they enter the equation for the density. It turns out they enter the equation for the density at higher orders in gradients than here. So they will enter, if you do if you carry this to further orders in gradients, you will get effects of theta even in the density equation due to interactions. Yeah, so but it won't come from rates of change of theta. So supposing you freeze the thetas, even then you get this. And supposing the thetas on some scale are uniform, not even. But what I'm saying is, okay. Yes. No, that's not right. So I have to write down an equation for the theta for Q. I have to write down an evolution equation for Q, which I have not done, which I will do. I told you that the evolution equation for Q is less interesting. You get alignment, and you get rotational relaxation, and you get coupling to density. So eventually, I'm going to give you a stochastic equation for both. I'm getting the deterministic part first. No, in fact, they will both be stochastic because the density, supposing I didn't have this, supposing I just had diffusion, even then the equation is stochastic. I'm right now writing down only the average equation. I'm writing down the average equation, but so right now what I'm doing is like writing down hydrodynamic equations, not stochastic hydrodynamic equations. I wanted to do it in steps. Next, I will tell you what the noise in this looks like. Even if you didn't have this, you know you should get that Dean noise, del dot. That's one part. If you have this, you get something slightly more complicated. I'll come to that. Then I'll tell you this theta equation. Then I'll tell you, in principle, I can tell you how interactions affect the density equation. Interactions affect the density equation, it turns out, through terms that come in with more gradients than this. So I'm just doing it in steps. At leading order in gradients, this is all that happens to rho, apart from noise. There is a Q equation which takes the form that I already wrote down last time, but which I can write down now if you like, if I can pull it out of my notes. Well, I wanted to actually stress just the evolution of the density, because all the novelty in the dynamics of this equation, okay, one other novel feature is that when you write down the density equation, just like I told you for the VIII model going to toner 2, when you write down the order parameter equation, the term that promotes ordering again turns out proportional to density. And again, it turns out to have some consequences. But my purpose in this lecture was only to show you how this term goes, so I concentrated on this. And the way this term comes in, at the moment you can see it actually comes in with no independent parameters in front of these two guys. Because I've taken a very simple model where the only diffusion the particles execute is along their length. The overall isotropic part of the translational diffusion will happen because on long time scales theta disorients you get. If you like, that's already been buried here by saying that to the extent that, sorry, W you should think of as just rho times Q is equal to rho times the object that I talked about earlier as the nematic order parameter. Okay? And that's what you get here. So the point of this exercise was only to show you how this term arose, and it was actually very important in that analysis to show you that I didn't need aligning interactions, I didn't need anything. This arose only as, just like diffusion is a determinist, diffusion of a density is an average effect of the evolution of the density conditioned on some initial inhomogeneity. This has a similar status. But the reason that it's sort of strange is the net result of this is that if you have an initially curved configuration, you get a drift. So that's why I sort of said, okay, we can do the alignment, we can do all that. The only thing I wanted to concentrate on is what appears to be a purely kinematic fact. It's just because of this, right? And of course, even that's, I'll tell you, it's a little misleading in the following sense, that it's not just a consequence of anisotropic diffusion. It's a consequence of the fact that a move of this sort, supposing I wrote down dynamics like this, but with inertia, okay, and I've got a particle, then it will be a particle with more kinetic energy this way than that way. And that would be manifestly not equilibrium. If I wrote down a particle like this in a confining potential, then again, I could say there's something weird about it. But if I wrote down something like this, or let's say I relax it a little bit, I write down something with a probability of moving this way and a lesser probability of moving this way, for example. I can always, if I only have a single particle, and I say x dot equals eta, and let us say eta x is some dx delta of t, I could always rescale out the effects. This is not really a problem that in a non-trivial way breaks detail balance. Because I've put in neither an inertia nor a confining potential, so I can always rescale out this difference. But if this is taking place in the presence of other particles, then the move becomes I align with my neighbors and then I move. And the time reverse of that becomes I move and then I align with my neighbors. So somehow at finite density, when there are other particles present, only then does this kind of asymmetry manifest itself in a real breaking of detail balance. And that you can see, in some sense, it's only when you take this term, see this term as written down, only makes sense to talk about this in terms of the nematic order parameter if there is some mechanism for developing a local nematic order parameter. This is just a descriptor. If I take n and multiply it by f and average it, I get q plus a half the unit tensor, and I can say that that's, q is involved. But in fact, in a system with no interactions, there's no Q. So it's, you need something to pull out the non-equilibrium aspects of the effect of this. And that is, so it's a little weird if you think about it. Purely from definitions, all right. So I hope I haven't confused people. I did something very, very simple. I just took particles that were preferentially moving back and forth in an unbiased way along an axis. And that axis itself is defined by the orientation of the particle, so that axis has a dynamics. And I asked, what's the collective dynamics of the density in that situation? I could relax this and have particles, as I said, that move along and transverse with different probabilities. And the only difference is that instead of getting this term with coefficient 1, I'll get this term with probability for moving along the length, and I'll get a modification of the diffusion with probability moving transverse. That's about all. Nothing else will happen. Yeah. Same thing. This is the same density. Yeah, yeah. Yeah, so now I will state without calculation that if you, okay, so have I confused or, okay, yeah. Where is K? Oh, I'm sorry, K is this K. I'm saying I can take my distribution function and take different circular harmonic components of it. K, if I do K equals 0, I just get integral d theta f of x theta t. Just like in the Boltzmann equation, if you integrate the distribution function over the velocities, you get the density. Here, just listen. If I take, in the Boltzmann equation, if I take f of x, v, and t and integrate it over v, I get rho of x and t. Here, if I take f of x, theta, and t and integrate it over theta, I get rho of x and t. That is why the k equals 0 equation here is just the equation for the density field. But because of the presence of these guys, the k equals 0 equation involves k equals 1. Because it involves k equals 1, it involves the density, the nematic order parameter. And k equals 1. F of x theta, I should have written this. Did I not write it anywhere? I seem not to. This is just like, I had somewhere earlier I had told you that if I take f of x, theta, and t. So you just think back to Boltzmann equation. F of x, v, and t, if I integrate it over v, that gives me, so integral of f of x, theta, and t, integral over theta, is rho of x and t. Integral of f of x, theta, and t times e to the 2ik theta, 2I theta, that I'll call f1 of x and t, and that is related to the nematic order parameter in a slightly complicated way, because it is, it is the following, that basically I could have taken something, I could have taken this object, but in this complex notation, I am instead taking cosine 2 theta plus I sine 2 theta. There are, when you've got a 2 by 2 traceless symmetric thing, you can package it as a vector in this way also, because it has only 2 independent components. And so then this object gives you the same information. So this guy is the moment you get by taking cosine 2 theta plus I sine 2 theta and multiplying it here. You can take this guy, and then you can pull out these guys. And you can reconstruct your Q tensor, and it'll look like this. The only thing is this F should be thought of as related to rho times, because it's got the density. It's F is sort of, it's rho times the Q tensor. That's the only difference. So the last thing I want to do, which I guess I can't do, I'll just have to assert. I was boasting that I was going to derive these equations with noise. So let me refer you to David Dean's paper for how the stochastic equation for the density has noise, or maybe if you give me 2 minutes, let me just tell you. Can I tell you in 2 minutes? All right. Supposing we take the simpler problem of just particles diffusing, independent Brownian particles diffusing. Okay. Then David Dean showed some 20 years ago the following. So you have n independent. He did it for a more general case, but let's take n particles that don't know anything about each other. Okay, with positions xi and evolving under the action of so I labels the particle, different noises are uncorrelated to each other, This is a vector. Its different components are uncorrelated to each other. It has strength 2D and it's uncorrelated in time, right? N independent Brownian particles. So what Dean said is, let me look at the quantity rho of x and t, not averaged, but just sum over particles, delta of x minus x. This is supposed to be big X. I of t. If there was only one particle, then normally you build the Fokker-Planck equation by taking this guy and averaging it. We won't average it. It's like if you're doing quantum mechanics, suppose you had a bunch of particles, each one's position is an operator. This would be the density operator. Not the density, but the density operator. Likewise, this is the density random variable, not the average density. And what does it do? Excuse me? Any snapshot, it will be that's all. But, you know, we're used to that. Sorry. I'm saying we do that all the time, right? Actually, when we're deriving, any time you want to derive hydrodynamics from a particular description, if you think of your particles, whether you think of them as hard spheres with a sharp edge or actual points, in all those cases, you have an unsmooth density field. A snapshot of the density field is unsmooth. So you will implicitly, you're doing that, even though you don't really say it. And that is a question, actually, because what Dean does is to come up with an equation, a description in which the systematic part of the motion comes from the microscopic pair potential. The moment you coarse grain, the pair potential is replaced by minus the direct pair correlation function, and you do liquid theory and all that. But we are not doing any of that. What we are doing is throwing away all that and just looking at end particles. So it has all the weaknesses you mentioned. So what he wants to know is, what is this? And we can guess that one part of that dynamics is going to be this. But that can't be the whole story, because these guys are random variables, so is this. Plus what? Okay. And, oh, by the way, before I go further, the reason I stopped here is that I've actually derived this. Sorry, before I forget Dean for a minute. This is the term that we wrote down by pure thought a lecture or two ago as that weird current. Okay, so I've shown you that current itself follows from just the stochastic part of the dynamics. Okay, that is an aside. That's over. So I'll just do this very, very quickly. Actually, I think it will take a little too long. Let me just assert the answer, okay, and let you read it. Let me tell you what Dean shows. What Dean shows is that this ends up, the noise is where eta is a spatiotemporally white noise. And he does this, let me not do the algebra, you can just go through it. The point is that he starts with this, he works out the dynamics of this, he finds a strange noise, I mean a noise that doesn't look obviously interpretable, and he points out that noise, I can tell you what the noise is. I'll just give you one step before the end. The noise he actually gets is, let's call it h of xt. I'll tell you what rho I of xt is. Okay, where rho I of x, and this is sum over I, rho I of xt is the density of each particle treated as a tag particle. Delta function only at the location of particle number I. Okay. The noise he gets is this, and what he shows is that this can be rewritten as a noise which no longer makes reference to individual particles. So there is, if you start with this, differentiate and patiently do the kind of thing you do to derive Fokker-Planck, but don't average, you'll get this noise in the equation for the collective density. That equation, the collective density has an object with the density fields, singular density fields of the individual particles, times the original noise driving the microscopic equation. And he shows that this can be rewritten in this way. And this is really interesting because, in other words, what it says is that multiplicative noise is a very ordinary, practically banal thing, and it happens just because if there's nothing there, there can be no noise. I mean, if these are, unless there are negative things. Okay. And this turns out to be useful in lots of ways, mainly in making your life harder for calculations. And so for the nematic problem, what we get by a similar but more complicated argument is, in this case, let me rub this out now. That's the definition. You can't read it from there probably. It's this. That is the noise he gets. As I said, you take this density, you build its equation of motion, you find that what you get is this noise. It's the noise in the collective, in the PD. That is, remember, what's he doing? He's taking n particles. He's building a number density field. It's a stochastic number density field. If you just carry out, sort of turn the crank, you'll find, actually without any real difficulty, that the net effect of that equation will be you'll get this, and you won't get this, you'll get this. Here, okay? And what Dean shows is that this guy is equivalent. Sorry, I shouldn't have said it like this. This guy is not equal to this eta, this guy is equivalent to this guy. There's several steps involved. So you get, this is what you get. Sorry, I should have, again, please correct your notes. I didn't mean to say that this is the same as this guy, same as this guy. Yeah. You have to, yeah. Right. No, I mean, look, you'd have to, he does the whole thing using Ito calculus. Okay. And so this, correct. And this noise likewise has to be interpreted as Ito. So this eta is Ito. Yeah. And if you do it differently, there's actually a paper, Kumaran, the chemical engineering guy at IISc, worked out what you would get if you wrote down stochastic PDEs for critical dynamics with noises that depended on the field variables. And I think he maybe even works out what it would be in each case. And in there as well as here, you're helped by the fact that you're at thermal equilibrium. So you know what, for example, for this problem, you would like the free energy functional for the density to be, since it's non-interacting particles, it should just be the ideal gas guy. It should be okay, and this comes out. So you are constrained by something, you're constrained by thermal equilibrium. I'll just tell you that a similar consideration gives you this guy plus noise, and that noise turns out to be not, let's call it something else. Where K is something which squares to plus our friend W, which is rho times Q, and H is unit weight. H is a vector, excuse me. The reason this is important is this term, so I'll really stop here. I know I'm eating your time up. So all of this is in that paper by us in 2013. If you look at this term, I'll just end with this. This is grad alpha, grad beta, rho q alpha beta, which I can think of as grad alpha Q alpha beta grad rho plus this bit is anisotropic diffusion. It says that the current due to a density gradient has a component dictated by the local anisotropy. This guy, together with this guy, says that the net current has a purely isotropic piece plus a piece that respects the anisotropy imposed by the local Q tensor. Nothing non-equilibrium about that, provided the noise compensates in exactly the right way. This noise compensates in exactly the right way. I can rewrite this as rho times 1 plus Q. I got it right? Yeah. 1 plus 2Q. Okay. This guy, this plus this. Remember, this is isotropic diffusion. This is anisotropic diffusion with anisotropy dictated by Q. This noise precisely takes care of that. Again, you have to do something because it's a multiplicative noise. So I think here again it's Ito. Okay? So this is a noise which when squared doesn't give you a density, it gives you, when squared gives you density times 1 plus nematic autogram. The Dean case would be no Q. Okay? This piece, however, is totally different, and that anisotropy doesn't compensate. So this piece is new, and this is the curvature-induced current that we and it's non-equilibrium. And the other thing is here, if you put in interactions in the continuum, then the free energy functional will have the interaction part as well. But yeah, meaning it's just an add-on. Yeah, the interactions aren't the complication. The noise is the complication. I'm saying that the interactions don't in any way affect the analysis about the noise. I mean, other than exclusion. So that's that exclusion on a lattice, I don't know. I would say the interactions, supposing you just have particles with a pair potential of some kind. That pair potential will come in so in such a way that the chemical potential, which here was just log rho, will now be log rho plus a kernel times delta rho. No, exactly. I'm saying the chemical potential. I'm saying you'll still get the d rho over dt is the divergence, minus divergence of current. Current is a mobility, is a density times a mobility times a chemical potential gradient. The chemical potential will have not only what comes from this, but what comes from the interactions. So what you will get is, so all that is there in Dean's article. But anyway. Yeah. Yeah, passive, yeah. Yes, yes. Yeah, that's the point. The point is that I don't know of, I'll tell you the fact is the following, that I tried to say that a few minutes ago, which is that anisotropy in the microscopic noise by itself can't give you non-equilibriumness, okay? So you're absolutely right, one should be able to cook up a model of this sort with anisotropic diffusion and yet equilibrium. In the coarse-grained theory, I know exactly how to do this. In the coarse-grained theory, if I have a noise whose covariance looks like this, and I have a diffusion that doesn't look like this, it has this term, but it doesn't have this term, that will describe your particles, equilibrium pneumatic. But this, taking a VIII style model and making it apolar in this way produces both anisotropy and non-equilibriumness at the same time. And I don't know what to do about it. Yeah, but somehow there's something. Okay, first I would say there's something I don't understand. What I don't understand is how to take models of that sort and do the treatment in a properly equilibrium way. I have two guesses for how to do it. One is I start with inertia. I put in anisotropic mobility therefore anisotropic noise strength, but the ratios being the same scalar, which we call the temperature. And then do the elimination of the velocity to get the effective. And there's some sort of, ultraviolet cutoff issue there, right? Because if you have two different mobilities, that means you have a Stokes time of one value for movement in this direction, another value in this direction, and taking the, there's some weird maths there because there are two different ultraviolet cutoffs in time, one having to do with this Stokes time and this one the other this Stokes time. I'm very nervous about taking them both to zero. So I have to think a little bit. Okay, it's a good question. I haven't really spent a lot of time on it. So I don't know how to take this absolutely minimal VIII style Chate Ginelli-Montagne model and produce something where diffusivity is anisotropic, but nothing is non-equal. There's got to be a way of doing it. It's obvious that if I had a parameter, so supposing I was writing down this theory by pure thought, I'd write down this term. If I was doing an equilibrium thing, I'd write this down, I wouldn't write this down, I'd be perfectly happy. It's obvious that this model is marrying those together in a somewhat extreme way. And it must be because the model is not sufficiently general. It's also obvious that somehow there's some prescription involved because the breaking of detail balance has to do with the difference between moving and aligning and moving. So I have to think, all this is going to be immortalized on YouTube or something. So my waffling about not knowing this or not knowing this is all going to be a matter of permanent record. So I'm quite worried. So, but there you are. It's a good question. I've been worrying about this for 14 years. It's because I'm lazy. Probably I should have done something about it. I should stop before I